Alright, this is part 2 of the video on time value of money. Continuing right along with where we left off last time. Let's go through number 15. If I can find it. Oh, that's my recording. I don't want to do that. Go back to the problems here. It says if you deposit $15,000, right here, number 15. If you deposit $15,000 per year for 9 years, you make each deposit at the beginning of each year in an account that pays an annual rate of 8%. What will your account be worth at the end of 9 years? Well, that's just the future value of an annuity due. 8%, I believe, in 9 years, and interest compounds annually. That would just be that from the lecture notes. And so you would have 202,298 at the end of the 9 years. Not a bad amount of money. Putting 15,000 in, getting 8% a year though, which is a reasonable interest rate. You're going to have to take on a little bit of risk, though, to be able to get 8%. $16. You plan to accumulate $450,000 over a period of 12 years by making equal annual deposits in an account that pays an annual interest rate of 9%. Assume all payments will occur at the beginning of each year. What amount must you deposit each year to reach your goal? Well, we know if you deposit an amount P each year for, and I always forget right away what the question was. 12 years, 9% interest, 450,000. You put P in at the beginning of each year for 12 years at 9% interest. And at the end of 12 years, the account, it said, will have 450,000 in it. So we're just figuring the future value of an annuity due and solve for the payment. Solve for the annuity. What's P? What amount do you need to put in every year? Well, that would just be 450,000 divided by this right here, obviously. Hopefully you can see how simple these formulas are to use. The math, it looks a little complicated, but it's just a formula. All you have to do is calculate it. It's not really that bad. So don't get scared when you see time value of money stuff. 20,498 rounded to the nearest dollar. That's what you have to put in every year if you want it to have that much in it at the end of 12 years. $17. $17 is another Newton's method one. It asks for what's the annual rate of return. Whenever you have an annuity and you're asked for the interest rate, it's going to be a Newton's method. If it's just a single amount and they ask for the interest rate, you can solve it, right? You can solve like we did, taking the natural logarithm and taking e to the power of both sides. You can solve for the interest rate. Whenever you have an annuity, there's not going to be a closed form solution for the interest rate. You're going to have to use some approximation method, such as Newton's method. So we won't do 17. Let's do 18. You plan to buy a car that has a total drive-out cost of $25,700. You will make a down payment of $3,598. The remainder of the car's cost you'll take out a loan for, and you will pay the loan off at the end of 5 years. You will repay the loan by making equal monthly payments. Your quoted annual interest rate is 8%, with monthly compounding of interest, obviously. The first payment will be due 1 month after the purchase date. What will your monthly payment be? Well, let's figure out how much money you're borrowing first. The car costs $25,700 and you make a down payment of $35,998. So what's the loan amount? Well, it's whatever the car's value is minus your down payment, 3,598. $22,102 is what you're borrowing from the bank. And they're going to lend you this $22,102, and you're going to make monthly payments at the end of each month. So we have an ordinary annuity. And the interest rate is per year, the annual rate is 8%. So from the bank's perspective, you reason. There are two options. They could take the $22,102, don't give it to you, put it in an interest-bearing account that bears interest monthly at 8%. At the end of 5 years, the account would have this much in it. Or option 2 is they could lend you the $22,102 and every month get P from you. At the end of every month, you pay them P dollars. Immediately, once they get that P dollars from you, they take that P and put it into that same interest-bearing account. It gets interest at this amount per month. Let it sit there. Then at the end of those 5 years, at the end of those 60 months, that account will be worth that much. They're indifferent between these two if the ending account values of both options is the same. Solve for P. P is the amount that you would pay per month. P is the amount that makes the bank indifferent between doing these two. So that's the amount they're going to charge you per month. So we quickly see then that P is equal to, whoops, not to the power of 12. 5 years times 12 months, 60 months in 5 years. There's 60 compounding periods in 5 years if interest compounds monthly. So P would be that divided by 22,102 plus 0.08 over 12 to the power of 60. That's what your monthly payment would be. All of this put into your calculator. Approximately $448 per month. Do 19. You will see that these problems become increasingly difficult. 19 is Newton's method again. They're asking what is the quoted annual interest rate you will pay with the lease, and this is an annuity. Excuse me. Leases are annuities, right? Because you have to pay a certain amount every period, whether it be month, week. So we won't do 19. Let's do 20. You are valuing an investment that will pay you $12,000 the first year, $14,000 the second year, $17,000 the third year, $19,000 the fourth year, $23,000 the fifth year, and $29,000 the sixth year. All payments are at the end of each year. What is the value of the investment? They messed up in the question here. What is the value of the investment to you now if the appropriate discount rate is 11%? So we have 6 years is the horizon. There's couple ways to think about this. The investment is worth we're indifferent between getting the 12,000 get 12,000 the first year. If we get 12,000 the first year, at the end of the first year, then we have, what's the interest rate? 11% per year. If we get 12,000 at the end of the first year, then we can put it in an account and get 11%, but we can only get it for 5 years, right? Because there's a 6-year horizon and we got it at the end of the first year. Plus, we can get so at the end of the 5 years, that amount would be worth this. I'm sorry, at the end of 6 years, that would be worth this. And then we can get the, where is it? 14,000 the second year. At the end of the second year, we put it in the account. that bears interest at 11%. But we got it at the end of the second year, so it only gets to get interest. It only gets to accumulate interest for us for 4 years. Plus the 17,000, which we get at the end of the third year, so that we only have 3 years left to get interest on it. Plus, what do we get at the end of the fourth year? 19,000, 23,000, and then 29. 19,000 at the end of 4 years. We can put it in the interest-bearing account at 11%, but we only get to get interest for 2 more years. 23,000. Put it in. We get it at the end of the fifth year. We only get 1 year of interest. And then we get 29,000 at the end of the sixth year. We don't have any time to get interest on it. What's the value of this investment to us right now? Well, here's the value of that account if we did that investment, right? And then we're indifferent between that or just getting an amount right now, call it P, investing it in an account that gets 11% per year and letting it grow for 6 years. And at the end of 6 years, that account would be worth this. Set them equal to each other. If the two accounts or both have the same amount of money in them at the end of 6 years, we're indifferent between the two. Solve for P. So P then equals 12,000 times 1.11 to the power of 5 divided by 1.11 to the power of 6. That just leaves 1.11 to the power of 1 on the bottom. Plus 14,000 times 1.11 to the power of 4 divided by 1.11 to the power of 6. That leaves 1.11 to the power of 2 on the bottom, and so forth. Now, so P equals, this is the present value of this investment to us, right here. And this looks really familiar to you. We're just doing discounted cash flows, right? But how did I derive this? I logically work through the intuition up here in the line before it, above it. Now, it turns out I'm not going to put all of this into my calculator. I could. There is a simpler function on your calculator that will help you do that. If you go to your apps on your TI-83 or TI-84, hit the apps button, choose the first app, which is finance, and then the seventh option, hit the number 7, which is NPV, net present value, and it'll pop this up on your calculator, and then you have to type something. The first thing you put is the interest rate. And you put it, don't put 0.11, put 11. So that's the syntax. Then you put a comma. Then you put your initial cash flow today. Well, nothing happens initially. You get the 12,000 at the end of year 1. So nothing happens initially. Then you put a comma. Then you put a little squiggly bracket. And then you put the cash flows. 12,000, comma, 14,000, comma, 17,000, comma, 19,000, comma, 23,000, comma, 29,000. Then you close the squiggly bracket. Then you put a comma, you open another squiggly bracket, and you put the frequency of the cash flows. The 12,000 happens once, the 14,000 once, 17,000 once, 19,000 once, 23,000 once, 29,000 once. The frequency in terms of how often it happens consecutively. Like if we had 12,000 at the end of year 1 and 12,000 at the end of year 2, you just put a 2 right here. Right, and then you close the parentheses and you hit enter. And that'll calculate this for you. A little faster than typing all this into your calculator. When you do that, you will get 76,274 rounded to the nearest dollar. And this is the calculator syntax. Go to apps, choose option number 1, then choose option number 7, which will be that, and you click enter and it pops that up on your screen. It'll pop up NPV like that, and you just type the rest of the thing, and this is what you type. This is all what you type for the rest. Right here. So that's number 20. No, that's number 19. Let's go on. Actually, that's number, what are we? That's number 20. We didn't do 19. 19 we needed Newton's method for. So let's go on to 21. You are valuing an investment that will pay you $27,000 per year for the first 10 years. Whoops. Yeah, there we go. $27,000 per year for the first 10 years. $35,000 per year for the next 10 years. And $48,000 per year the following 10 years. All payments are at the end of each year. If the appropriate annual discount rate is 9%, what is the value of the investment to you today? You're going to do the same, what is it, 27, 35, and 48. You do the same logic as we did up here. Same thing as 20. You're going to find that, and I've already forgotten, 27, 35, 48. You're going to find that you're going to be doing this calculation. (1.1 to the power of 2 plus 27,000, this 1.11 to the power of 10 plus 35,000, 1.11 to the power of 11 plus 35,000, 1.11 to the power of 12 plus all the way up 35,000 to the power of divided by 1.11 to the power of 20 plus then 48,000 divided by 1.11 to the power of 21 all the way out to 48,000 divided by 1.11 to the power of 30. 27,000 the first 10 years, 35,000 the first 20 years, 48,000 27,000 the first 10, 35,000 the next 10, 48,000 the final 10. We can simplify this on the calculator really with using this NPV function. So you do it, you go to your apps, choose the first option, then choose the 7th option. It'll pop up this on your calculator. Put 11. Is that the interest rate? 9%. Sorry. Put a 0.09 everywhere I put a 11 there. 1.09. 9% is the interest rate. I was using the previous problem's interest rate. Sorry. So put the 9%. There's no initial cash flow. The first cash flow happens at the end of the first year, and you get 27,000. Then open a squiggly bracket. Put the first cash flow 27,000. And the next one 35,000. And then the final one. Then a comma, then a squiggly bracket. The 27,000 happens the first 10 times consecutively. Then the 35,000 happens 10, and then the 48,000 happens 10. Close the squiggly, close the parentheses, and hit enter. And it'll quickly calculate this for you, so you don't have to put all of this into your calculator 30 different times. That would be too much. $323,123. For those problems that are more real world, where you're not putting the same amount in every time, when you have more money, you save more money, right? Or you invest more. When you don't have as much, you invest less. So that matches your sort of the cash flow situation that most people would find would happen to them, versus just putting in the same amount every time. Whenever you have that, then it's hard to do it with an equation, but an Excel spreadsheet comes in really handy. Increasing difficulty here. So number 22. John and Peggy recently bought a house. They financed the house with a $125,000 30-year mortgage with a nominal interest rate of 7%. Mortgage payments are made at the end of every month. What is the total dollar amount of their mortgage payment during the first 3 years that will go towards repayment of the principal? Every time they make a monthly mortgage payment, a portion of it goes towards principal and a portion of it goes towards interest. In the early years of the mortgage, a much higher proportion of their monthly payment will go towards interest than towards principal. And in the later years of the mortgage, in the later months of the mortgage, a much higher proportion of your monthly payment will go towards principal versus interest. This just reflects the risk that the lender has to bear. Early on in the mortgage, it's very risky. The lender knows that they're not going to get their $125,000 back for another 30 years, right? So early on, they're going to require a much higher, of your monthly payment, a much higher portion of that's going towards interest rather than the principal. And then later on in the mortgage, towards the end, the lender, you've paid them for the last basically 30 years, and it's not as risky to them. They've already collected most of their money, so they don't charge as much interest. So in other words, the portion of your monthly payment that goes towards interest is much smaller, and a much larger portion of your monthly payment is going towards knocking down this principal, this $125,000 that you originally borrowed from them. So that's the idea here. Now, you think that you have to set up a spreadsheet to do this, but in fact you don't. The first thing we have to figure out is what's the payment every month. What is the payment that you have to make to the bank every month? And again, we reason from the bank's perspective. They can take the $125,000 and don't lend it to you. They could just put it in an account that bears interest monthly, and since that's how much you would pay them per month if they lend it to you, since that's how often you would pay them if they lend it to you monthly, the one option is don't lend it to you, just put it in a monthly interest-bearing account that it bears interest at 7% per year, but interest compounds monthly, and leave it in there for 30 years. At the end of the 30 years, that account would have that amount in it. Option 2 is they could take the $125,000, give it to you right now, and then at the end of every month require you to pay them P dollars, your monthly payment. When they get the P dollars from you, they immediately put it into the same interest-bearing account. It's going to get this amount per month. They do this for 360 months, 30 years, 30 times 12. And at the end of the 30 years, that account would have this amount of money in it. The bank's indifferent between these two alternatives if the values of the two accounts are equal at the end of the 30 years. And therefore, we can solve for your monthly payment. They're going to charge you the amount P that makes them indifferent between these two. And you can quickly see that P is equal to this divided by this, right? We'll call this A and this B. I don't want to write it. A over B, which is approximately, if you do the math, you put it into your calculator, you're going to get approximately $861 a month. All right? So that's how much you're paying the bank every month. But that wasn't the question. The question was, what is the question? What total dollar amount of their mortgage payments during the first 3 years will go towards repayment of principal? Well, if they're paying $861 a month, we're not going to answer it right here, but I'm just going to do a little calculation. Then after 3 years, they will have paid the bank back this many dollars. The question is, of this, how much went towards principal and how much went towards interest? Well, they only asked how much went towards principal. And I can tell you that it's not 50-50. In the early years of the mortgage, the first 3 years are the early years, if it's a 30-year mortgage. In the early years of a mortgage, at least for the first half of the time length of the mortgage, there's going to be a higher percentage of the monthly payment going towards interest than to principal. And as we go on, the relative percentage change. It starts out almost like this. And it kind of like this, right? And eventually it shifts till at the very end it's like this, right? Hopefully you saw that you visualize that. But they're asking for the actual dollar amount here. How much of this $39.96 went towards principal? Now, you can get at this using a spreadsheet. You can set up a spreadsheet with several columns, and you can figure it out. But you can actually get at it another way. Just reason logically. I'm going to write down, rather than just say it, I'm going to write down. Reason like this. The bank is indifferent between you giving them unpaid principal after 36 months. So whatever you haven't paid, the principal, what did they lend you? They lended you $125,000. Whatever you haven't paid of this $125,000 after the 3 years, you've paid some of it. Some of this $39.96 went towards the principal and knocked this down. But whatever you haven't given them, so whatever the balance is of the unpaid, whatever the unpaid principal is after the 3 years, the bank's indifferent between you just giving them that right then, because they can take it and invest it and make, what's the interest rate? They can make 7% per month. Or, I'm sorry, 7% per year divided by 12, the monthly interest rate. They could just take it and invest it for the rest of the time if they wanted to. They're indifferent between that or getting your, or continuing to get your $861 per month payment for the rest of the 30 years. I'm sorry, for the rest. How many more months after 36 months are there? In 30 years, there's 360 months. And if you have 36 months go by, then there's 324 months left, right? So the bank can take your unpaid principal, call it P, which is what we want to know. If we can find out how much of the principal after 36 months you haven't paid back, then we can figure out how much in the first 36 months you did pay back. In other words, how much out of this total amount you paid the bank, how much of it went towards principal. Right? Let P be the unpaid principal. Let's call it UP. This is what you haven't paid the bank. Of the $125,000 in principal, after 36 months, this is the balance, what you haven't paid them back. They're indifferent between you giving them that right then, just give it to them then, and they can take it and invest it and get 7% per year, compounded monthly, for the rest of the 324 months. At the end of that account will be worth that. Or just getting your $861 per month. And as soon as they get it at the end of every month, they just put it into that same account, get the 7% per year divided by 12 for the monthly rate for the rest of the 324 months, minus 1. And at the end of the 30 years, that account will be worth that. They're indifferent between these two if the two accounts would have the same value at the end. And we can solve for UP, the unpaid principal. Right? So then UP equals this big mess right here. Divided by this big mess right here. Hopefully that makes sense to you. And if you solve, you're going to see that after 36 months, the principal that they haven't paid is, yeah, because I can't even remember. Calculate it. Go back and look at my calculation. $129.08. And then you round it to the nearest dollar. It's $129.09. So after 36 months, you haven't paid $120,909 of the principal back. So after 36 months, how much of the principal have you paid back? Well, it's whatever the principal was originally, minus that's whatever's left unpaid at the end of the 36 months. So at the end of 36 months, you have paid $4,091 against the principal, approximately. So now you see how much of your, in the early early years or the early months of the lease, how much of your monthly payment goes towards principal versus interest. Not very much. In the first 30 years you paid, in the first 3 years you paid $30,996 to the bank. Of that, $4,091 went towards principal, and we can quickly calculate how much went towards interest. The other $26,000 went towards interest. Question 23. You are valuing an investment that will pay you $26,000 per year for the first 9 years, $34,000 per year for the next 11 years, and $47,000 per year the following 14 years. All payments are at the end of each year. They don't tell you what the interest rate is, though. They just tell you how much you're going to get every year and how many years. And but they don't tell you once you get that money, how much interest you can get on investing it in some investment. But they do tell you that another similar risk investment alternative is an account with a quoted annual interest rate of 9%, but interest compounds monthly. What is the value in today's dollars of the set of cash flows you have been offered? This investment that you're offered it's a yearly thing. Every year you're able to put $26,000 into it, which means interest would only compound once every year on that investment. For the first 9 years, every year you would put in $26,000 at the end of every year. And so at the end of the first year you put in $26,000. It sits there for a year. At the end of year 2, you're going to get interest on that $26,000. Plus you're going to put in another $26,000 and so forth. So interest compounds annually. That's the implication here in this investment. They tell us that another similar risk investment alternative has a 9% quoted annual interest rate, but interest compounds monthly on that one. Well, yeah, if interest compounds, this is a little ambiguous. I said that the original investment they're implying that you would only be able to get interest once per year. And I think that's correct. But we don't want to use 9% though, because this other rate, everything I've said is right so far. Sorry, I'm a little indecisive here, but yeah, what I've said so far is right. The question is, what rate do we use for this original investment to try to figure out the present value? We don't use 9%, I can tell you that, because this other investment alternative, this similar risk investment alternative, interest doesn't compound annually, it compounds monthly. And so what's the real interest rate we get on that other investment? What's the effective rate that we get? The rate that, if we calculate the rate of return on that other investment, what we have at the end of the time period in the account minus what we put in at the beginning divided by the beginning, what would that rate be? It would be the effective annual rate. That's the rate we want to use in valuing this initial investment, this one that they're asking us to value. So what's the effective annual rate of interest here in this case? So let's figure that out. We know that we take 1 plus the quoted annual rate divided by the number of compounding periods in a year, which is 12 if it's monthly, raised to that number, then subtract 1. So the effective annual rate of interest on the other alternative is 9.38%, basically. That's the rate we want to use in valuing the investment that they're telling us about, right? And then how do we value the investment that they're telling us about? We do the same thing that we did in those problems before, where we calculate MPV. We're basically going to just do MPV. We're going to put in 9.38, nothing initially. Then we get 26,000 for the first 9, and 34,000 for the next 11, and 47,000 for the next 14. 26, what was it? 34 and then 47. Thousand, sorry. Thousand, comma, squiggly. The 26 happens 9 times, and then 11. The next one happens 11, and the 47,000 you get for 14 consecutive years. So 9, 11, and 14. Close parentheses, and hit enter, and that'll calculate. It's just like doing what we did number 20 and number 21. I went through, this is what you're actually doing, but to simplify the calculation, you can put it into your calculator, just like 20 and 21. And you will find that the number is, don't know for sure. Let's have a look at my calculations here. $314,518. Rounded to the nearest dollar. So you can check yourself to see if you get that. Approximately. If you don't, then it's because I've rounded this interest rate right here. I think this is like, so this is really 9.3807. This is 07. All right, let's move on to the next one. Looks like my battery is about to die, but I'm charging, so it should be okay. So number 24, you have just won the Georgia lottery with a jackpot of $40 million. Your winnings will be paid to you in 26 equal annual installments, with the first payment made immediately. If you feel the appropriate interest rate is 8% annually, what is the present value of the stream of payments you will receive? This is similar to calculating the monthly payment on a mortgage, home mortgage, right? We have two alternatives, right? We could get the, we can get the 40 million. It's going to be paid to us in 26 equal installments. So we could take the 40 million divided by 26, and that's the amount that we put in every, was it year? Yeah, every year. And what would that investment be worth at the end of, what would that annuity be worth at the end of the 26 years? Are payments made at the beginning of the year? Yeah, but the first payment made immediately. So payments are made at the beginning of every period. So we could, at the beginning of every period, we could take that amount that we get, 40 million divided by 26. We can invest it, get 1.08 times the 1.8 to the 26 minus 1 over 0.08. Interest compounds annually. At the end of the 26 years, that annuity would be worth that much. All right? Or we could get an amount now, call it P, invest it at 8% interest per year, let it sit in that account for 26 years, and at the end of 26 years, that account will be worth that much. We're indifferent if the two account values at the end of 26 years would be the same. Solve for P. And that is what the what this annuity would be worth to us right now, the present value of the annuity. So we just take this and divide by this. And you will get, let's see, 17,961,194. Rounded to the nearest dollar. That's the present value of this annuity to us, as of today. just to show you from lecture notes, we can use, I keep saying that we can use that formula. That what would this be? This would be the present value of an annuity due. Let's just use the present value of an annuity due formula, and you'll see we'll get the same thing. Right here, this formula. The P in the formula, whoops, sorry. The P in the formula here, this P would be it would be that steady, it would be the annuity, right? The 40 million divided by 26. It's a decimal. I don't even want to write it as a decimal. I'm just going to write 40 million over 26. If you do that, and then according to the formula, we take it times 1 plus r, and then times 1 minus 1 plus r to the power of negative n over r. So times 1 plus 0.08, then times 1 minus 1.08, power of negative 26, negative n over 0.08 over r. Is it over r? Yeah, over r. So if you did this calculation right here, you should get exactly the same thing as if you did up here. You should get this. You can verify that. All right, 25. How much time do we have? It's getting down to 15 minutes here in a sec. You have just won the Georgia lottery with a jackpot of 11 million. Your winnings will be paid to you in 26 equal annual installments with the first payment made immediately. If you had the money now, you can invest it in an account with a quoted annual interest rate of 9% with monthly compounding of interest. What is the present value of the stream of payments you will receive? It's the same thing as what we just did. So same thing as 24, except we don't want to use this rate because interest compounds monthly. Careful, careful, be very careful. You get this amount, you get your 26 payments every year, right? That's what you get it every year, annually, right? If it says here, if you had the money now, if you had all of your winnings, all of your 11 million, if you had it right now, you could invest it in an account with a quoted annual interest rate of 9%, but that account would have monthly compounding. So what's the effective annual interest rate on that other account, that alternative account? That's the interest rate we want to use when evaluating this present value of an annuity due right here. So effective annual interest rate, again, you take 1 plus the quoted rate, divide that by the number of compounding periods in a year. If it compounds monthly, there'd be 12. Raised to the power of the same thing, minus 1. And I think we just did this already earlier. I think you get 9.3807%. Didn't we just do this up in the problem up here? Right here? Yeah. So that's the rate you want to use. And then you do the same thing as in problem 24. You can either use the present value of an annuity due formula directly from lecture notes, or you can do what we did right here, right? So if we use the formula from lecture notes, then we would have, what was it, 11 million, 26 equal payments, 1 plus 093807 to the power times 1 minus 1.093807 to the power of negative 26 all over 0.093807 close, and you calculate that and you're going to get an answer of 4,453,790 rounded to the nearest dollar. So you're using the effective annual interest rate here. And then And 26, you're planning for retirement 34 years from now. You plan to invest $4,200 per year for the first 7 years, $6,900 per year for the next 11, $14,500 per year for the following 16. Assume that you're going to do all the investments at the end of each year. Every time you put money in, it's going to be at the end. If you believe you will earn an effective annual rate of return of 9.7%, what will your retirement investment be worth 34 years from now? Well, we can do this in 2 steps, actually. Right? How to explain this? We're doing number 26 here. We are indifferent between, we don't have a net future value calculation on in your calculator. You don't have a net future value. You have net present value, but not, you can discount back to today's dollars, but you can't figure out the future value, the net future value of something like this, where here the amounts are different, right? It's not the same. If this is the same, you just use the future value formula. But it's not an annuity. An annuity is a steady stream of equal fixed payments. Here they're unequal. 4,200 is different than 6,900 is different than 14,500. So you can use a spreadsheet, but that gets a little tricky. That just takes too long, especially on an exam. So we need to recognize, though, that whatever the net future value of that is, if we calculate that, the value of that account, putting 4,200 in, making 9.7% per year, do that for the first 7 years. Then in that same account, you put 6,900 in every year, and you're making 9.7% every year on that account. And then in the same account, you're putting 14,500 in every year for the rest of the 16 years, and you're making 9.7%. Calculate the future value of all that. What's the value of the account at the end of 34 years? Whatever it is. You're indifferent between that account or just getting an amount now and investing it at that effective annual rate, letting it grow for 34 years, and you'll have that amount. You're indifferent between these two numbers. And this right here is the present value of, as we've seen from the previous problems, what is this P? It's the present value of the cash flows that you were told about, of the investment that you're offered. We can figure out the present value of those cash flows because we have a present value way of thinking, right? There's the present value shortcut on the calculator that I've taught you, and we can actually just do it by hand. It's just we don't have the future value shortcut. And I haven't really taught you how to do the future value by hand if it's different numbers if it's not an annuity. So we can recognize that you're indifferent between these two, right? And this P is the present value of these cash flows. So all we have to figure out is the present value of the cash flows multiplied by 1.097 to the power of 34. And that is going to be that future value. The value of that account at the end of 34 years, which is what they're asking for. So we calculate the NPV, the present value. We can do it with our calculator using the 9.7% payment. Cash flows happen at the end of every period, so nothing initially. And then what was it? 4,200 for 7, and 6,900 for 11, and 14,500 for 16. Comma, open a new squiggly, 7, then the 6,900 happens for 11, and then 14,500 every year for 16 years. Calculate the net present value of that using your calculator, using your the app on your calculator. Remember, that's just the same thing as doing 4,200 divided by 1.097 to the power of 1 plus all the way out to 4,900 divided by 1.097 to the power of 7, because that goes 7 years, plus 6,900 divided by 6,900 divided by 1.097 to the power of 8 plus 6,900 divided by 1.097 to the power of 19, right? Because it happens for 11 years. 18, sorry. Right? Plus 14,500 divided by 1.097 to the power of 19 all the way out. 14,500 divided by 1.097 to the power of 34. You do all that in your calculator. It's 34 different things put into your calculator. 1 and 2 and 3, 4, 7, 8, 9. Put all those in and calculate. You're going to get the same thing as if you just do this. So just do the shortcut, and you end up getting, what is it? 60, let's see. 66,240 if you round to the nearest dollar. So that's the present value. That's the first step. That's this P. Then we take that and multiply it by 1.097 to the power of 34. Because you're indifferent between this, whatever that future value of that account is worth to you right now. If you got that right now and you just invested it, making 9.7% every year for 34 years, you're indifferent. The value of the account at the end of 34 years would be that. And you would be indifferent between that and if it's equal to the value of that other account, that weird annuity where you're putting in 4,200 for the first 7 years, 6,900 for the next 11, and so forth. The future value of that account, if the two are equal, you're indifferent. And so we can solve for what the future value would be, right? By just taking the present value of that account times the 1.097 to the power of 34. And when you do this calculation, you end up getting 1,542,217. So that's the future value of that. At the end of 34 years, you would have $1,542,217 in your account. So 27, and then we're done. All right, this one I'm going to draw a little picture for. You plan to retire 33 years from now. You expect that you will live 27 years after retiring. You want to have enough money upon reaching retirement age to withdraw $180,000 from the account at the beginning of each year you expect to live, and yet still have $2,500,000 left in the account at the time of your expected death, 60 years from now. You plan to accumulate the retirement fund by making equal annual deposits at the end of each year for the next 33 years. You expect that you will be able to earn 12% per year on your deposits up until you retire. But when you retire, you only expect to earn 6% per year on your investment, since you will place the money in less risky investments. What equal annual deposits must you make each year to reach your retirement goal? So in these 33 years that you're working, you're going to be making equal annual deposits into your retirement account. How much do you put in there if you want this to reach this goal? Let's draw a little diagram that describes what we were just told here. For the first 33 years, let's have a look here. Yeah. We'll call this now t equals 0. We earn 12% on whatever we put into the account. We're going to put in the same amount every year. If it wasn't that way, then this would probably be much trickier. But we're talking about an annuity here. So we're putting in the same amount every year. We're going to get 12% on whatever we put in every year. We're doing it we put it at the end of every period. I think it said the end of every period. Let's check. Find that out. At the end of each year, yeah, right here. So, and then we retire right here. And then this time period is 27 years. expect to live 27 years after retirement. This is t equals 60. This is death. As bad as it sounds. We want to have 2,500,000 left. Exactly. It didn't say at least. We want to have 2.5 million in the account when we die. And during this period right here, we're going to take out 180,000 at the beginning of each year. We take it out at the beginning of each year. After we retire, we're taking out money at the beginning. It says that here. You plan to withdraw 180,000 at the beginning of each year once you retire. However, the money that's sitting in the account is still getting 6% interest every year. We must, when we retire, we must take all this money in this account and put it into another account that only gets 6%, not 12%. It's less risky. We don't want to lose too much. We don't want to lose all of it when we retire because we're not working. We can't put anything back in there. So we're just living off the interest, basically, the money and the interest that's in there. So it's getting 6% interest. We're taking out 180,000 at the beginning of every year. The question is, what should our annual contribution be to our retirement account for each of these 33 years? That's the question. Let the amount of our contribution for each of those 33 years be P. We're putting in P each year. Then at the end of 33 years, what do we have sitting here? Well, we have P. It's the future value of an ordinary annuity, right? It did say that interest compounded annually, right? Yeah, it didn't say anything about monthly or anything like that. So at the end, we'll have that much. Right? When we retire, we will have that much money in the account. Now, let's assume that we didn't take anything out once we retired. Now, what does this amount grow to when we die? This amount is what's sitting there once we retire. Remember, we take this amount out, put it into a different account, and we're making 6% on it every year. So this is just like a single amount that we take out once we retire and put into an account that makes 6%. So what's the future value of this amount once we die? It would just be that times the 1.06 to the power of 27, because we leave it in there for 27 years after we retire. And when we die, this is what would be in the account, right? But we know, and we want that to be equal to 2.5 million. Right? When we die, we want it to be equal to 2.5 million. Whatever is in the account, we want to be 2.5 million. But we know that was assuming that we didn't take anything out once we retired. But we know we do take stuff out. We take out 180,000 each year at the beginning of each year. And if we would have left this 180,000 in, it would be getting 6% interest each year. So it's like there's an annuity of 180,000, and it's annuity due, getting 6% interest every year. For 27 years. If that would be the value of that annuity, but that's what we're taking out of this account. And so we subtract that. I don't know how to. If we didn't take anything out, if we retired and put that money into a 6% interest-bearing account and let it sit there for 27 years, then when we died, we would have that much money in the account. But that's assuming not taking anything out. But we are taking stuff out. We're taking out 180,000 at the beginning of each year from this account. That's equivalent. How much are we taking out in total dollars over the 27 years? This much, right? Because that's equivalent to an annuity. Because this 180,000, if we didn't take it out, it could be growing at this. At the beginning of every year, we would get the 6% interest, and this happens. It's an annuity, right? It would be growing like this. This would be the value this is the value of an annuity of taking $180,000 and putting it at the beginning of every year into a 6% interest-bearing account. Since we're taking it out of this 6% interest-bearing account, this is the value that we're taking out. So we just subtract that. Put that right here. So all of this minus all of this needs to be equal to 2.5 million. Solve for P. Remember, P was the initial amount that we're putting in for each of those 33 years at the beginning while we're working. And solve this for P. So we'll do that. You'll quickly see that P equals 2.5 million plus this plus this, and then we want to divide by this right here, right? And you might be surprised at how little we have to put in every year if we want to reach our retirement goal. If you calculate this, well, relatively how little. To me, it seems like not very much, but maybe to someone else it is. It's a lot. $8,875 if you round to the nearest dollar. So we put in $8,875 into an interest-bearing account that gets 12% every year. We do that for 33 years. Then when we retire, we don't have to put anything else in. We can take our account, transfer it over to a 6% account. We can take out $180,000 every year to live off of. And then when we die, we'll still have $2.5 million in our account. All of that can be accomplished by just putting in this $8,000 per year, this basically $9,000 per year into the account. But the account has to be getting 12% per year, and we have to do it for 33 years. So this ends the video on time value of money.